thanks everyone for coming and joining this talk, because we are very fortunate today. We have visitors. We have a visitor from Germany, particularly from the University of Bayreuth. Probably some of you are familiar with Professor Prof Doepper when we had that online workshop with the University of Bayreuth. But today we're going to hear more about what Professor Doepper is doing, particularly in the research that he's working on. But before I gave the floor to Frank, just a quick introduction. So Professor Frank Doepper, after he studied the mechanical engineering at RWTH Aachen University, Frank began his career at the Fraunhofer Institute for Production Technology in Germany before moving into industry. So it's good to hear, let's say, that we're going to hear experience from someone who worked for the industry as well as doing research. And in the last 20 years, Frank has worked in technology and investment management and as site and production manager for international companies before he was appointed professor at the University of Bayreuth. Obviously, today we're going to hear those experiences as well as more details of the work that Frank is doing. Over to you, Frank.
Thank you very much, Alan. So I hope that you can hear me. Just look into the on the monitor. Yes, thank you very much, Alan, for the introduction, and thank you for giving me the time to share some of our research activities with you today. As Alan already said, I come from Germany, to be more precise, from Bavaria, which is a southern part of Germany. The Bavarians say that it's the best part and the nicest part of Germany, but the others say that too. And yeah, luckily you're in different continents, so we have no conflict there. And Beirut sounds more dangerous than it is. I'm not going down this road, but we often have some. Sorry, is there? Okay, yeah. Good. That's better now. Good.
I'm just going to check the cameras.
Or you have to restrict my movement area.
It can't follow me, but following Alan right now. Oh, right. Oh, yeah. Oh, that
Is it?
Yeah. Yeah.
Okay. We have to move. So.
Yeah, focused on it. There we go. Yeah.
There we go. Okay. Ah, yeah. Now it's moving. Yeah.
Yes.
I have to chop this out later. Yeah.
And this is recording. Okay. No. Do we want this recorded?
Not recording?
If you want to record it, I'm easy with that.
Okay, you've got pretty much from here
to
that table.
Okay.
You can run around.
Thank you. It's like in the zoo without a fence. Yeah.
Yeah, you just get the exact plan. No, the recording's going.
Okay, it is, yeah. Okay, it's already.
Sorry, we've had issues in this room before, so it's better to get it all right now.
Okay. So Bayreuth is not as dangerous as it sounds. In Germany, you pronounce it Bayreuth and not Beirut. It's a town with around about 75,000 people living there. We have a university with around about 12,000 students. So the share of students in the city life is quite good. And I would like to share some topics that we are working on at the moment. My chair is called Manufacturing and Remanufacturing. So one topic, as the name says already, is the topic of remanufacturing. How can you give technical products a second life? And the other topic that we are involved in, I heard that in Springfield, this is a topic as well, is additive manufacturing. Or as we call it, additive innovations, because we say manufacturing is just the doing, but behind it, normally there's hopefully an innovation. So we start quickly with the remanufacturing topic, or here a quick glance at the University of Bayreuth. I have to look at the monitor so that I know what you see. This is our campus, which is a bit green as well. We have 6+1 faculties. I say 6+1, the last one, life science, nutrition and health. It was just founded 5-6 years ago. And I just learned when we were driving across the campus that this is a topic here in Toowoomba too. Apart from that, mathematics and physics, biology, chemistry, law and economics is a big topic in Bayreuth. Linguistics, literary studies, cultural studies, and for sure, the most important faculty, engineering science. This is the faculty that we belong to. In total in Bayreuth, we're around about 280 professors. We have, as I said, some 12,000 students and 2,600 employees. The Faculty of Engineering was founded in 1995. We have around about 800 students, 300 employees. It's 24 chairs at the moment. I think it's still correct. And we have around about 20 million euros third-party funding. This is, if you would translate it to Australian dollars, or if you would change it, it's around about $40 million per year, which for Bayreuth University is not such bad because the overall third-party funding is 60 to 70 million. So with just 10% of the professors, 10% of the chairs, we bring in around about 1/3 of the third-party funding, which is important in Germany. We just discussed it quickly during the tour because we mainly finance our researchers by third-party funding. So when we don't have third-party funding, we can't employ researchers, and only quite a few heads at the chairs are financed by central money. Most of the heads have to be financed by projects. 6 bachelor and 10 master programs, but I'll share the slides afterwards with you. And if you want any further details, I can also share the links with you. Yes, this is where we work. I always say it's the gatehouse to the university. Either they didn't want us on the campus or there was no space. I think the official version is there was no space. So we had to, when we were granted a building, move just to the entrance. You can see there where the sports area is. That's the entrance road to the campus, the main entrance road. And we're situated just opposite the entrance. And as I show here, it's a friendly and peaceful cooperation of University of Bayreuth, my chair in this case, and a Frauenhofer project group. This is not uncommon. Fraunhofer is more dedicated to applied research, so we tend to work closely together with the industry, get the impulse from the industry, what they need, what their needs are. And on the other hand, on the university, we are more dedicated or inclined to basic research. I would say the border is not a strict one, and so the cooperation of both institutions is not uncommon in Germany. Similar as you said, when you're going next time to Augsburg, it's also cooperation of the university there and the Fraunhofer colleagues. Fraunhofer, just a short information. If we read in the newspapers in Germany, the Fraunhofer Institute has done this and that, we always ask ourselves, who was it? Because it's some 70 institutes in Germany, and we have some offices abroad as well, but mainly it's focused to Germany. So it's a wide range of R&D activities that Fraunhofer is following there. Yes, some drilling down what we are doing at our chair. Additive innovations, as I said already, sustainable production and circular economy. And then there's also a topic, I'm not going down this path too much today because I think it's not too interesting to you, data value creation. Similar as you experiences, whenever you have a process, a production process, there's a lot of data being generated. What do you do with this data? Is this data in the future more valuable, more important than producing the material product itself? This is a topic that we are looking at, and when you're manufacturing, you try to understand the processes. In the past, we worked a lot with design of experience to try to fully understand and mathematically, statistically go through the processes. That's not always possible. When it comes to additive manufacturing, you don't maybe understand all the physical principles behind the process. And so AI, as I like to say, is plan B if design for manufacturing or design of experience doesn't work, or it is too slow. And so this is one path that's becoming more and more important. Machining in general, that's something that all the manufacturing chairs do. It's milling, drilling, sawing, cutting, and we are here dedicated especially to some niches like cutting wood, for instance. But today it's more about remanufacturing and additive innovations. Remanufacturing, just a short glimpse at it. The idea is that you have a technical product, you take it apart, you inspect all the parts, you might exchange parts that are not good anymore, and then you assemble it again and give it a second life with the quality being as good as it has been before. And it's a very important part of the circular economy that we are trying to deploy in Germany, in Europe. It's something that the people want, but it's also something that's driven by the official side, by EU regulations, EU laws, and then all these EU laws or EU measures that are defined in Brussels, they are put to the European countries, members of the European Union, and have to be translated into national law. So more and more you have laws coming up that motivate and force manufacturers and also people selling goods to get them into any kind of loop. For instance, when you return your car, it is taken apart, the material, the steel is recycled, but there's also newer regulations. You have the right to have your product repaired. The European regulation has been launched a few months ago. National translation of it will come soon. That means if you have a broken coffee machine, for instance, and you go to, I think you call it Harvey Norman's here, it would be MediaMarkt in Germany, and you take it there and say, it's broken, and then the sales people would tell you, I have a good offer now, but give me your old one, I'll sell you a new one. You will have in the future the right in Europe to say, no, I want this one repaired. And then they have to repair it. I don't know if when it's 20 years old, if it still applies, but just as an example, step by step, the topic of circular economy is built up, especially in Europe and in Germany. There's also a strategic aspect to this. When it comes, for instance, to electrification, you need a lot of batteries. You need lithium-ion batteries, which are used in automotive, for instance. And the material that you need for these batteries, you can't find them in Germany, can't find them in Europe, or just a bit in Europe. And so we have to import this material. And the idea is that if you fill the system with a certain amount of these critical metals, for instance, and you can establish a circle, then you become independent of the import of this material. So it's the topic, is it good for the environment? Is it good for the movement between your fingers? So does it financially make sense, but also does it strategically make sense? If we look at the remanufacturing, where is it used today, then we have, I would say, some traditional industries. Some of them we've listed here, and also one topic is the automotive sector. As you know, automotive sector is a big topic in Germany. If you take the automotive companies, I would say they are the largest employers in Germany. VW employs some, I think, 300,000 people only in Germany, followed by Mercedes and BMW with around about 80, 90, 100,000 people. And this is only the people that are putting together the cars. If you think of the value generation that is done at a car manufacturer, that's roughly, let's say, 20–25%. So you could say on every worker in a car factory, you have 3 workers that are supplying the car factory. So it's a few million people working somewhere around the automotive industry. And I'm not saying too much, but maybe we should have been a bit more progressive when it comes to alternative drives for cars. So the topic of combustion engines has been followed for a long time. And you have a lot of components here that you used in the past and where also remanufacturing was established well, not only for trucks, but also for passenger cars. And now we are seeing a big change there. Why in the past did remanufacturing already make sense? Just an example of a starter motor. You get in an old one, you take it apart, you replace the parts that need to be replaced, like rubber parts or bearings. And if you look at the material consumption that you can save and also the environmental effect, then you have a lot of savings on the environmental side, but also on the cost side. On the cost side, it's roundabout a value of thumb. You could say it's round about 50%. You don't get to the 88% as on the material side, or sometimes the environmental effect is going up to 70% as well in terms of savings. Why? Because it has a lot to do with manual operations. So whereas production of new products is highly automated, remanufacturing today still often is linked with a lot of manual processes. And this costs more money in terms of work, in terms of labor. And so the financial effect is not as high as the effect for the environment. We've listed on the right side the classic process chain for remanufacturing. And this is completely different to manufacturing new products. You do as good as possible an initial check. But you get a box of, let's say, used starter motors, and you have to take them or leave it. It's not as with new production where you get a big box and you test 3 parts. They're not good. You send it back completely, as it is used in the automotive industry. Here, at the other end of the lifetime of a product, you have to accept it. You try as good to check, but the final idea, what the condition of the part is, of the core is, as we call it, you only get when you completely disassemble it. You have to clean everything. You have to examine and sort the components, rework them or replace them, and then you reassemble it. So it's a completely different process. If we look at the changes in terms of branches, this is the picture as we see it in Germany and in Europe, but I think it's not so different to what you experience here. We have a strong move into renewable energy. We've shut down our last nuclear power plant 1 year ago, and it's financially doesn't make sense to ramp them up again. So we are running completely without nuclear power. This is not quite true. We are running completely without German nuclear power. So we're importing, we're moving to the next line, the e-mobility. This is what is a big topic, energy intensive industry as well, because electricity is quite expensive in Germany at the moment. We have a new government. I heard that you've voted as well. And a big topic in Germany is how do we bring the economy up again? How do we accelerate it? How can we reduce electricity prices? Information communication for sure, aerospace and defense is coming up as well. You know that we don't have completely peaceful times in Europe. It's the Ukrainian or the war in Ukraine, which is ongoing, and I would say target for all European countries in terms of expenses of their GDP in defense is 5%. Poland already does it because everybody is getting prepared. If Russia wants to do further steps, we have to be able to defend our freedom. Let's get back to e-mobility. And we are looking at 2 topics there, the batteries and then the traction motors. And this is maybe not quite up to date because due to energy prices, electricity versus petrol, maybe it's slowing down a little bit, but further, sooner or later, this is going to be the picture in terms of cars, at least passenger cars. We are moving towards 100% electrification. It was the target to be there by 2035, also by national laws. which said we ban cars with combustion engine as of this date. And then for sure, this is the perspective at the top of the sold cars, and at the bottom it's the fleet. I don't know exactly, but the cars, they get 10, 11, 12 years old in average at the moment in Germany. So when the whole fleet will be electrified, it will take a bit longer. And here we have, this is from a consultancy company, the move from components that you don't need in the future anymore, that are under pressure, so to say. We have transformers that are changing, and we have rising stars that are becoming more and more important. Under pressure combustion engine, fuel injection systems, all these products, which is not good, because there's a lot of know-how that has been established, especially in the topic of combustion engines. V6 from BMW, very nice sound, very nice car, not popular in the future anymore. Transformers, brakes, they get smaller with electric cars, thermal management, and also gearboxes. There's a big company producing automated gearboxes, ZF in Germany. They're producing gearboxes with 9 gears, very nice. Don't need it if you have an electric car, that's a pity. Thermal management, also a change. When you have a car with combustion engine, the water pump runs as soon as you start the engine. It stops as soon as you shut down the engine. We have a company in Bayreuth which is producing water pumps for electric cars, and they say the life expectancy of these products has to be 10 times higher than the water pumps for the conventional cars. Because the thermal management has to run and to operate when the battery is charged, when it's in use. So it's a complete different situation. Rising stars for sure, electric motors. A lot of automotive suppliers are jumping on that. And traction batteries, with the situation, you don't have one battery manufacturer in Germany. We are all importing these batteries. So that's the idea, as I said. How can you then keep it in a circle? And here's another idea of what the aftermarket potential of BEVs will be in 2040. And you see there's a high share of traction batteries, followed by electric motors, power electronics, and thermal management. So the expectancy that it's going to be a big market to take care of products that might get a second life or might be recycled as to the material is big. If we look at traction batteries, the number or the amount of batteries that will be returned in Europe per year by 2040 is expected to be 1.5 million tons. That's quite a lot. And for sure, you don't want to put them to landfill them. They're much too valuable, so you have to find ways what to do with these batteries coming back. I think the average guarantee that automotive manufacturers give you for these products are 8 years at the moment. And this is a big challenge, because customers say, what happens after 8 years? Is my car broken then? So there's a lot of people that see this as a risk at the moment. Remanufacturing in terms of battery systems maybe is a bit different to the strict definition as to the British standard. You would be happy here if you achieve 90% of the capacity then again. And a big topic is also the difference of the quality or the capacity between the cells. Because also new manufacturing of the cells is not that stable. And if one cell in a module is not good anymore, this will impact the performance of the whole module. I just show you the full picture. So we have the vehicle, we have the high voltage system, we have the battery module, and we have the battery cell. And this is what we are looking at. How do you get the battery with electronics out of the car? Today, it's mainly done manually. How can you disassemble the battery system? This is today also done manually. Here, this is a picture, and I'm not starting the YouTube video now. It's too risky for the presentation. But if you search this, or if you type this in or search Frauenhofer IPA demo BUD, then you'll find it on YouTube. it's a robot that disassembles battery system automatically. And then you have the modules, and this you can only do up to date by hand. So you see the colleagues here wearing the safety gloves, trying to get the battery cells out. We started some projects in this direction. One was together with other universities and also another Fraunhofer Institute. GreenBud, the idea was to derive guidelines for remanufacturing of batteries. What would the design of a battery have to look like so that you can remanufacture it in an easy way? This is a project that was funded by a federal ministry in Germany. And the general strategy is you can either swap modules, because an HV system is consisting of various modules. You can swap cells, or you take it all apart and then you sort the cells as to their quality and state of health and put them together again. But this would be the most work, the last path. So at the moment, number 1 and number 2, so module swap and cell swap, that's, if at all something is done, is what is done. And again here, if you want to do it, you have to disassemble it, which might be challenging, clean it, inspect it, remanufacture it, and reassemble it. And the disassembly, I'm just jumping to the next slide, is a problem because there's no standard how they are assembled. There's no standard as to how the cells are put together. You often have some kind of mass that the cells are put into for mechanical reasons, if they should become larger, and also for thermal reasons to get rid of the thermal energy. And so it's a big problem to disassemble these parts. And big question, how can you automate it? This was a prototype that we derived from this project. So a modular approach, you can exchange the individual cells. But again, this is not necessarily in line with a, let's say, cheap manufacturing of these cells. It makes sense over the whole lifetime, but not for the first lifetime. Robotic non-destructive disassembly, as I said, is a big topic, A, for financial reasons, but also for health and safety reasons. You have the topic that the batteries might catch fire, and it's very hard to deal with these fires. This is something which is very prominent in the media. I think statistically there's more cars with combustion engine burning down in Germany, but you don't make it to the media, don't make it to TV. If you have an electric car, especially Teslas at the moment, which are not very popular, then this is shown everywhere. It goes viral, as we say. And this again is just a picture of the robot that we have developed there with special tools to automatically disassemble such a module, as you can see here. Yeah, that is a quick look at the traction battery topic. And when it comes to electric drives, it's a similar question. What can you do to get them into a circle? And here it is a bit easier because it's a, I would say, classical technical project. And we started with a small electric drive. We started with an electric bike drive. The electric bikes have overrun the, as we call them, bio bikes. So bikes where you have to do the work yourself. It's around about 2-point-something million electric bikes sold in Germany and 1.9 something bio bikes. And we had a project together with some industrial partners, but also some other institutes on how to give an electric bike drive a second life. The rule of the games are the same. You have to disassemble it, and then you have to see which parts you can still use. Here are some pictures about it. We also have, I think it's unfortunately only in German, a little report about this. And here, the potential of reducing the global warming potential was up to 90%, because a lot of parts you can reuse. There are some parts like these gears which wear. Luckily, these gears are made of polymers, and so we were able to reproduce them by additive manufacturing, which is another of our hobbies. We also try to involve some modern inspection technology, like a camera inspection, which finds out which type of drive do I have, and then you get the work instruction how to deal with this specific drive. And this is a bit more complicated than also when you're manufacturing new parts, because the old parts, they might be dirty, there might be some corrosion on it, and still the camera has to detect, is it the right part, is it this part? And then you have to open it like that or the other way around. This is where we use AI. Then the product disassembly for the test line that we established is still manual, cleaning of components, inspection, sorting, reworking, replacement with additively manufactured new parts, and then the reassembly. That was a small product, and now we are actually working together with a supplier, Schaeffler, which is a big automotive supplier in Germany. And this is electric traction motor of a car. And they also are entering this market. And right from the start, they want to have the right approach and strategy, what they can do with their products, how they can use parts that are not right first time in the new parts production, but also at the end of the product cycle, what can they do with these parts, and is remanufacturing possible, and does it make sense? This is just an example of how many parts can be in an E-axis, and we looked at several cars, the Renault Kangoo, for instance. I haven't seen any of these on your streets. They are used for the Austrian postal service. And then when they come back, they take the batteries out. And if you have a solar power plant, they use these as stationary batteries. That was a project that we did with them together. Yes, these are the main aims of the research project. So try to conserve the value, develop automated processes, as I said already, and also design recommendations. But there you always have the conflict between, let's say, cost-efficient manufacturing of the new parts, and then looking at the end of the life cycle and maybe spend some more euros so that it is easier to disassemble it at the end of the lifetime. We have two dedicated labs in Bayreuth. One is what we call the Reman lab, the test or the product that we are using there for teaching, but also the process to go through with industrial partners, if it's possible for their product as well, is the electric drive. And then we have a high voltage lab, because you have a lot of, some people say we are quite good at regulations and norming and so on in Germany. And so if you want to work with high voltage systems, you have safety regulations that you have to follow mechanically, but also as to the training of the people. So in this area, only people are trained, or only trained people are working, PhD students and technicians, no students. In the Reman lab, this is something which is not as dangerous. We can use it for teaching as well. Yeah, this is what the Reman lab looks. So it's like a small production line, starting with the entrance diagnosis, disassembly, parts cleaning, and then the reassembly. And in the end, you have a bicycle with a remanufactured drive. Some other projects we are involved there, but I think the main topics I touched, and I will share it with you later on. Desire for electronics, we called it. It's getting into electrical appliances like vacuum cleaning, robots, and so on, how you can disassemble them, how you can detect also with camera systems and using AI if the parts are still complete, if all these pins are still there. This is topics that we look at, and then also which part is still suitable, where does it make sense to start the remanufacturing project and where not. Also this together with industrial partners like Drops Lab, which is a startup, or Captura. Yeah, some ideas for industrial projects, life cycle assessment for diesel engines, larger diesel engines is something that we're involved in. Then also when it comes to using AI, this is the middle part of a BMW SUV, and they had the designer had the good idea to make this board out of wood, and then they want to have the touch buttons or the buttons that you take a lot of wood off by laser milling, and so the light goes through, and then you can touch it, and then sat-nav will start or whatever. Problem is, wood is one of the worst materials to machine because it's a natural material, and you never know how thick the fibers are, how thin the fibers are. So the picture at the bottom was before the project, luckily, and we worked together with them to stabilize the process. Our colleagues had a look from the AI side with a camera system, a rather cheap camera system, and there the colleagues from our industrial partner, they were the laser specialists, and if you bring these people together, or if we brought these people together, it was possible to improve the process, and now it's working. AI-supported wear detection of machine tools is another topic. And then, as I already touched, raw material criticality of production process chains. We looked at it in medical technology, but that's also something that is important for the battery sector. Yes, I did it a bit faster because I think there's some colleagues here who might be interested in the second topic, which is additive manufacturing. I'm trying to share. No, doesn't want to share.
Enable, yeah, up the top on the yellow bar.
Ah, enable content. No, it's resilient.
That one is. And share this. It's already shared.
Is it? It's if you. Yeah, now it's working. Magic fingers. Now we just have to do the display settings, probably. Or swap. Ah, it works like that. Okay. So a quick glance at the topics of additive manufacturing. I'll jump over these because you know it already. We have three main techniques that we use, PBF, LB, M on the metal side, high-speed sintering on the polymer side, and fluid mix, which is for us a new area. But I'll go quickly through what we are doing there. On the metal side, we have two main machines, a Nikon and a Coherent, and some devices around it. This is also in a separate laboratory for safety reasons because we're working with titanium, and this might be dangerous, not if you inhale it, but it might lead to fires and explosions. And what we are investigating there is the application of particles, functional particles during the laser beam melting. Two use cases here. One, how can you reduce or avoid support structures? And the other one, how can you functionalize the component properties? And this is the setup we are doing it with. So we have a printhead integrated into our laser printer. And then we have the two paths that we follow. The one topic is we use an inkjet printhead after the recoater to generate a powder ink mixture, which then enables us to bring the thermal energy out of the part into the bottom plate without support structures. The function of support structures is not a mechanical one. As you know, it's just, or more or less, to get the energy out of the component, out of the heat, the zone where the heat is implemented. And the topic is, if we do it this way, we do not need support structures, and we can save the removing of the support structures. This is just an example of an impeller, and you see the traditional path at the top would be you have a lot of support structures that you have to remove afterwards. And if we do it with a new approach, with this ink particle mixture, you can just remove it easily and don't have so much work afterwards. This is just what the effects were. It was a PhD thesis that has been completed just earlier this year. So production time goes down, costs goes down. As to the material, we still have two paths. The one is the material costs or consumption would go up by around about 20% if you're not able to recycle the ink particle mixture. If you're able to recycle and you have the equipment, then material consumption would go down compared to the classical approach with support structures. And shape and dimension accuracy is even increasing. This is some pictures of that again. The other idea is how can you improve the material functionality by adding particles. And here, for instance, what we are playing with at the moment is how can you improve the hardness or the wear resistance of an additive manufactured part by entering ceramic particles, for instance. And this is what we do here with silicium carbide. I hope I translated it right, SiC particles. And we add these at the corner of the randzone, at the borderline of the part, but not in the middle. So the material properties stay the same in the middle of the part, but at the surface or near to the surface, you add these particles, and thus you generate a part with a higher wear resistance. The idea is to go further down further this, to follow this path further, and then, for instance, to increase ductility, wear resistance we already did, but also temperature resistance, and in the end, there will still some parts where the metallic base is unchanged. This is all just more details about that. And we are at the moment investigating where it can be applied: aerospace, medicine, automotive, or in the general engineering industry. High-speed sintering, a completely different technique. We have a machine here which is very open as to setting the parameters, and we can easily customize it. And there's also, compared to other manufacturers, like the multi-jet fusion technique, unrestricted use of materials as to powder and ink. The process looks like that. It's a powder bed based principle, but instead of having a laser that is then melting the particles and you're producing layer by layer your part, you have an ink that is applied. In the ink, you have particles that are absorbing infrared light, and you go over it with a lamp, and thus the energy is only absorbed or primarily absorbed by the areas where you have applied the ink, and thus you can build up a part layer by layer. The difference is, and that is why it's called high-speed sintering, the lamp moves over the powder bed with the same speed and just once. And when you have a laser, you have to scan the surface that you want to melt. And so you have identical times layer by layer. And all in all, you're faster than with laser technique. And what is an advantage as well, the duration of the heat introduction into the material is much longer. So you're working with, how could I say, lower heat intensity, and this might be useful if you want to process special materials. Might also be useful if you don't want to provoke aging effect onto the material. This is the advantage of this technique. It's provided by, as far as I know, two companies at the moment. One is Voxeljet, which is located in Augsburg, and the other one is Stratasys, and they call it SAF. Voxeljet calls it high-speed sintering. Stratasys, they call it SAF. And this enables us to use a lot of different polymers. This is just a selection that can be machined by high-speed sintering, cannot be machined by many other techniques, also going into HDPE or POM, for instance. One topic about the additive manufacturing is if you want to go to a design department and tell them we use additive manufacturing now, they have to get rid of injection molding, so they have to think the process new, and they have to get rid of their material. So it's two new topics, and what we try to do is reduce the pain of the design engineer. It's a new process, but you might use your old material. This is just some examples what we can machine here. The sole on the right side. Yes, I know Adidas has stopped manufacturing it, but that's the idea that you can machine also, let's say, complex geometrical structures. Just skip over it. What you can also do is by adding special particles, you can functionalize these parts. We did it with a bioreactor for tissue engineering for some colleagues, where you can install electrical conductivity, and you just do it in special areas that you want it. And in the others, you don't do it. And you can adjust the stiffness or the hardness of the material. We call it grayscaling. And as you can see on the right side of the picture, this concrete block has the same weight on the left side as on the right side, but the material or the part that we produced, even if it looks the same, if there's no concrete block on top of it, like the sole here, is softer on the left side than on the right side. And we do this in one printing job. So it's not two-component injection molding, it's one print job we do. And you can have soft, flexible on the one side and hard or solid on the other side. This is some of the ideas that you can do with it. It's just a lattice structure on the left side, but then it could be an insole for someone who has problems with his feet, where you can do it customized, and some areas are softer, others are harder. That's what we are working on at the moment, and also with industrial partners like Launhardt and AM Polymers, which are smaller companies in Germany. Maybe something more to play around with, functionally graded translucency. This is something which we found out, depending on how much ink you apply to the HSS process, you can also let light through or not let light through. And this is something which is at the moment maybe more a design feature, but could be something to customize products like dashboards in a car, which is very important that you have it individualized, not just with carbon fiber implants, but maybe also with something with your initials or anything like that. We're just playing around with it at the moment, but hope that we will find an industrial application there as well. FluidMax, just a quick glance at it. It's about parts that are soft, that are flexible. And we are just starting in this area. There's not a lot of printers available at the moment. We have a French brand that we are cooperating with there. But we see that it's interesting, and there's also some interest from industrial partners to 3D print parts that are flexible, like how do you call it? The rubber pieces you need for metallic parts. This is something that we are working on now. And there as well, you can mix the components and also produce parts that have conductive layers incorporated, but they're flexible. Sorry, you can't see that here in the picture. And the shore hardness we are able to produce at the moment is between 5 and 80. Additive manufacturing and circular applications. This logo, you know, which has been created by a student in 1970. Just to sort it a bit, we talked about remanufacturing, which is one of the R strategies. R0, we try to avoid as engineers because we say all our products are necessary, and so refuse is not an option. But what you can consider is R1 till R9, and R8 and R9, recycle and recover, we say should be avoided. The best is if you are moving somewhere in the dark blue area and trying to go from reuse to repurpose. And as a matter of fact, there's a regular report, the Circular Gap Report, and only 7.2 of the products that was in 2023 are in a closed loop. And we're not gaining, we're losing there. The year before it was 8.6%. So there's a big gap that can still be included in a loop. Why are we losing there? One example, electrification. If we are entering a new technology, you need to fill the system with new materials. Like lithium-ion batteries, you need a lot of materials that you have to take from nature and put it into the circle first. So we are not gaining there, we're losing at the moment, but you see how big the potential is to increase circularity, not for the environment only, but also in terms of financial aspects. When it comes to additive manufacturing, we called it the sustainability hat trick, and we said you have to look at the sustainability that you gain through additive manufacturing. So classical topics like lightweight in aircrafts, saving kerosene there, but also the sustainability in additive manufacturing. When we wanted to set up our first metal printer, our environmental health and safety guy came and said, no, you got to take care of this and that and that. And then we had to establish a complete lab around it, which cost as much as the printer itself. But then in the end, we felt better as well, and he felt better. And nothing is as bad as you can derive something from it. We are doing consultancy for 3D printing companies now, how to set up manufacturing environment correctly. We're talking to a lot of 3D printer manufacturers. We're not buying a lot of machines, but as we don't have so much money as a university, you have to talk to a lot of people to find the right machine. And some of the sales guys, they say they have customers and they are not entering their workshop because the way they are working with powder is definitely dangerous and they don't want to inhale it and so on and so forth. So sales people from 3D printers, they are not going to their customers' workshops because they say they are not doing it the right way. And as it is just being ramped up and all the topics of exposure to this small particles is gaining importance, we think it's also a big part of sustainability in additive manufacturing. And then looking at COVID and other topics, there were a lot of value chains that were interrupted. And I think the potential of additive manufacturing to at least temporarily close these value chains or supply chains has not been fully deployed. This is something that we call resilience in value creation networks. So these are the three areas of additive manufacturing. One example I already showed to you in terms of remanufacturing when we printed these gears. So we've done that. There's another topic which we did also with Tobias Rosnicek, for instance. He was involved in it, and also the colleagues from Holger Ruckdeschel. We called it monomat, so monomaterial. And the idea was that you have a cascaded use of materials. First, we used a powder bed based additive manufacturing process. Then the material, for instance, for products in the medicine sector or sports technology or lifestyle as well. Then the recycled material was used in material extrusion, MX. And then it went to injection molding, where you can keep it in a loop for a very, very long time. So it's not the best way of establishing circularity because it's not keeping it on the same level exactly, but the idea is to keep it in the system as long as possible. That was the aim of this project, for instance. And this was one of the test parts again. Unfortunately, we weren't able to manufacture a huge number of these shoes, so not everybody in the project could get a pair of sports shoes, but maybe in the next project. Resource efficiency also, how do you lose powder, where do you lose powder? And this is an investigation that we did, and then try to fight it and try to regain the powder or not lose the powder in the first place, because it's very, very expensive, not only in the metal area, but also in the polymer area. We're also working here with the organizations in Germany, like the Society of German Engineers, and are writing partly authors of these regulations, as I said, for instance, in terms of how to handle metal powders in additive manufacturing. And something that we started in Bayreuth as well, and that would be the end of my presentation here, the Campus Additive Innovations. Because, as I said in the beginning, we have 7 faculties in Bayreuth. And we started our activities in additive manufacturing some years ago, must be 2017, round about 2016, when I joined the university as well. And we found out that a lot of colleagues are working in this area. Not only engineers, but also lawyers, physics people, chemical engineers. And so we tried to get them all together. And it was, or at the moment, it's around about 30 chairs over 5 faculties, I think, that are active in the area of additive manufacturing. And we try to group it or to sort it into 5 groups or areas of activity. And as you can see, it's the classical topics of materials, processes, application and design, but also value chain and digitalization, and then business models and legal issues. Because if you're printing a part, either you have the CAD data or you can scan it. But if you scan it, did you hurt somebody's intellectual property or not? And if then you bring it into the market, what about the warranty or your responsibility because you brought a printed part on the market? This is topics that our lawyers like, we don't like, we just like it's technical possible, but that's the nice thing about Bayreuth. You have a lot of different perspectives on problems, and we're trying to make use of it as good as possible. So, sorry I was a bit fast there as well, but Alan said, let's try to get a look at both topics, and I thank you for your time. Hope that I could give you a bit of an impression what we're doing in Bayreuth, and it's just what's happening at our chair. But I heard that there's also connections to other chairs, and it would be great if we could improve this and increase the cooperation in the future. Thank you for your time.